All right. Good afternoon. It's 12 p.m., so we can go ahead and get started. My name is Matt Montgomery, Automation and Controls at Gardiner. It's an honor having everyone on here, and we thank you for joining us. Today we have Erich with TrueFit KMC to discuss the important role of airflow monitoring stations, the role they play within mechanical ventilation and equipment operation. It's important because the vital role airflow management has in maintaining indoor air quality, occupant comfort, and energy efficiency. A great man once told me, "You can't manage what you don't measure." And for those here that are responsible for indoor spaces, you know that building wellness and indoor air quality are two current industry focuses because fresh air exchanges with conditioned outside air are a fundamental component of pretty much all documented IAQ strategies. So anyone who has managed supply, outside, and return airflow probably shares in some of the industry pain, whereas it's difficult to balance high system performance and energy efficiency with any great deal of accuracy. Typically in airflow monitoring stations, they're installed in areas like inside hoods or too close to dampers or unfiltered air streams. And these spaces are not synonymous with reliable readings. And these have been some of the ongoing pains and frustrations around managing airflow. So TrueFit was designed and developed to address these accuracy issues. So we're excited to present this overview of the technology, and please fire away with any and all questions. We'll save a buck at a time in the end to answer them all. We truly believe we're on the verge of seeing a new wave of requirements for outside air verification. So without any further ado, please welcome Erich Kreuter.
Hello, everyone. Thanks, Matt. I'll echo a lot of his points he made in his introduction that we see across the industry. Typical airflow measurements have reliability issues or repeatability issues, and a lot of times it becomes a controls problem to either mask the symptoms or figure out a way to manage around these poor measurements, which led us to develop technology that was the basis of TrueFit. So for those that aren't familiar with TrueFit KMC, we are a US-based manufacturer. Our headquarters is in Indiana. We've been around for more than 50 years, producing pneumatic, analog, electronic, software, IoT, and now airflow measurement technology. So again, all USA made and supported here in the States. So to get right into it, why do we measure airflow, specifically outdoor airflow? And what are the kind of the common issues that we see with technologies that I think as an industry we use what we can and we put it where we have to, and a lot of times that leads to the not necessarily the most ideal situation and measurements. So let's look at kind of the pain point that we're trying to fix or address first before we go into the technology. When we talk to engineers and contractors out there, we ask them about specifically outdoor airflow. We get a few different reactions. Some people just set a minimum damper rate one time at a specific fan rate and say that that's good enough. Typically, they're giving up a lot of system performance and energy savings when they do that. On the other end of the spectrum, people that are interested in high performance sequences, a lot of times find that the existing technologies out there, whether it's pitot arrays or, as Matt mentioned, measurements installed in turbulent locations such as hoods or too close to louvers, don't produce the results needed to really drive those high performance building sequences where we want fairly precise control over pressurization and resulting ventilation. So both sides of the spectrum have issues today. Generally we're either losing OA on energy efficiency or we're losing it on system performance. So ASHRAE does a really nice job here telling us why OA measurement is critical. OA is the most expensive thing that we're bringing into our building most of the time. We either need to heat it up, cool it down, wring it out, or even add humidity to it at times. And all of these dynamics impact occupant health, comfort, overall system performance. And depending on what we care about as designers and supporters of high performance buildings, ASHRAE has several standards out there that tell us what metrics we need to look at. Whether that's 60 or 62.1 or 90.1 or some of the newer ones that deal with infectious aerosols and things like that in 241p. So ASHRAE gives us our guidance, and as an industry, we're relying on that guidance to produce or we suggest the best way to operate these buildings. So at the end of the day, every building is different. An OR is not the same as a school. So it's up to us as designers to balance energy efficiency, indoor air quality, I'll even say occupant safety now, and kind of build the best system that we can. The commonality here is that all of these systems and questions, predicate themselves on reliable and accurate measurement. So as I mentioned, pressurization is one typical problem we see in a lot of buildings. And a lot of that can lead from ventilation schemes that are not set up or measured properly. Over ventilation. I think we saw this a lot during the pandemic. It leads to a lot of wasted energy. It might be good for indoor air quality. It might be, in a lot of instances it is, but there are times where it might not be. But it was the easy answer. So I think as an industry, we're seeing it sway back to more of what proper ventilation would be. The most energy efficient thing would be to not bring in any outdoor air at all, but I don't think that's healthy for your building. And we see a lot of things in the green building era that was called sick building syndrome. But typically we see that with pressurization issues now. So mold, discomfort, things ingressing into your building because you're not properly pressurizing your space. And again, lifting a little bit out of the ASHRAE standard here is 170. Depending on the type of space you are, if they're critical environments, ASHRAE is going to recommend certain air changes per hour to make sure that space is properly conditioned and free of contamination. I will mention air changes per hour as the metric here. And as we talk to people, especially as new standards come out, Title 24 in California has some ventilation standards for schools and things like that. We get some confusion as, I'm already doing demand controlled ventilation. Why do I need to measure air changes per hour? And I'll say here that DCV is not necessarily ventilation. We're standing in a CO2 measurement for occupancy, but a lot of the new standards are wanting guaranteed airflow rates per occupant that is actually in the space, not a design load, and really driving those efficiency standards more in real time. So there's a reason why we don't see CO2 sensors in ORs and hospitals and pharmacies and things like that, because again, ASHRAE has decided that as an industry, we need to do air changes per hour to make sure that ventilation rate is proper versus a stand-in measurement such as CO2 or PM. So looking at a few typical issues we have, putting airflow measurement where we need to. One thing that we see a lot of times is, equipment today is getting smaller and smaller, and the ductwork installed actually, generally can be limiting as to where you can put proper airflow measurement. Typical install guidelines want laminar flow. That means so many duct diameters away from bends or elbows, veins, transitions increasing or decreasing. So there's a lot of restrictions that we would typically have to manage. In rooftops, especially, or unit ventilators, you wouldn't have any ductwork necessarily to provide that proper laminar flow, which again is an issue for existing technologies. And I think when we get into technology of how TrueFit works, you'll see why that's not an impact for our method of measurement. The other thing we see typically is on some larger air handlers where you might have a ventilation damper for outdoor air and an economizer damper. The trick here is we're not capturing the full amount of OA typically with a flow station. We're only capturing that ventilation amount, which as soon as we open that economizer damper, now we're not accurately measuring the air changes per hour that could be needed to actually control and ventilate that space. So Matt mentioned as an industry, we typically put the technology where we need to. A lot of times it's inside louvers and hoods and things like that. So these pictures here, I would say are pretty representative. Most people would agree that they've seen these type of sensors installed in these locations, which again, turbulent airflow. If a balance were to come in and take a measurement, ASHRAE says in 111 that if you don't have accurate measurements, you can't use a laminar flow-based measurement, and you need to use something they call the temperature ratio equation. And we'll talk about why that's important here in a minute. But know that a balancer couldn't take a measurement accurately in this in these situations most of the time. And if we dig a little deeper, we'll find that these types of sensors installed in these locations, typically, even from the manufacturers, it's no fault of their own or no fault of technology. We're putting it in a place that's not necessarily ideal. So the accuracies are going to get wider. The repeatability is going to get wider as well. And it certainly leaves a little bit more to be desired. One thing I'll mention that the high performance building sequences, they are pushing fault detection integrated in real time into more and more pieces of equipment. And a lot of the fault detection methods that ASHRAE is prescribing, again, are foundational on that ASHRAE 111 formula that we're going to talk about here in a second. That is an integral part to the TrueFit AFMS. So now we have a little background. Let's talk about the solution to the problem. So TrueFit Airflow Measurement Station. It is a system of components that provides reliable and repeatable outdoor supply and return airflow measurement for monitoring or integrated control. The measurement itself is based on ASHRAE standards, namely that 111 standard. And you'll see as we go through that the best way I could describe it is that we've automated a balancer inside that flow station. So the same calculations that he would do are the same calculations that we're providing in real time. So all of this data that we're going to show you, measurements of supply, outdoor, and return, as well as all the temperatures and pressures that are required, are available via BACnet, so they can be integrated into anybody's building management system. To give you a little lay of the land, we've got an equipment schematic of a typical installation on a rooftop, or small pieces of packaged equipment. So we'll see that the core of the system is that TrueFit AFMS controller there in gray. This is built on the backbone of our BACnet devices, so it's all native BACnet out of the box. And there's a few different sensors that are connected to it that give us all of these airflow measurement metrics. The first would be a supply air measurement. This is a velocity pickup where we're taking a total supply. The second thing is temperature measurements for OA, return, and mixed air. So we see that we have all three of those temperature sensors, and that lets us calculate those mixed air equation numbers. We'll talk about why those are important in a second. The new term here, a new component for most people, is something we call an inclinometer. This is a tilt sensor commonly found like in your car or a piece of agricultural equipment, but this provides us a repeatable position of where that mixed air damper assembly is. And once these components are installed, we have a measurement method called characterized airflow performance. So what characterized airflow performance is, it is a method where we generate a curve for the airflow going through your equipment for any given position of that mixed air damper assembly. This is very similar to a pump curve for fluid, where if we know the speed of the pump and we know the pressure, I can tell you the flow through. Here, the way it works for TrueFit is if I have my curve and I know the position of the mixed air damper assembly, that will tell me the percentages of OA and RA that are present in the supply airstream. The supply airstream gives us our total, and then we can break out the percentage based on that performance curve. This curve is a multi-point curve, and it can be programmatically built by the controller. It goes through a learn mode sequence. This takes about 2 hours to characterize all 3 of these airflows and the temperature and pressures, and after which we're producing the measurement with the curve, the inclinometer, and that supply airflow total. So a little bit more on the inclinometer. This is mounted potentially in the outdoor airstream. So it's a hermetically sealed, highly accurate device. There's no maintenance related to it. Unlike other measurement technologies that put pitot tubes or thermal dispersion sensors in the dirty air, there's nothing here that can get contaminated or need any ongoing maintenance. The benefit of having this independent measurement is that we know where we are in that performance curve at any time, irrespective of the linkage or hysteresis that would be caused by the linkage or the damper actuator. We've removed all of those inaccuracies from the equation. 111 is a little bit of a new standard to a lot of people. It's one of the standards the balancers frequently reference. So if you want to take a little bit of look under the covers later, there's a section of 111 that shows why we have to use the temperature ratio equation, mainly because of the lack of ductwork and unpredictable turbulence. So when a balancer encounters that situation, he's looking at this section to know, now I have to calculate this on temperature, which again is the same way that we use to programmatically build that pump curve for each individual piece of equipment. A little bit more on the learn mode, and then we'll give you an example of what that means very simplistically on that rooftop diagram. But we do want to see a delta T between return and OA in order to guarantee best accuracy. 10 degrees is the minimum, 15 degrees is better. And again, we want to make sure we maintain that delta T for approximately 2 hours. It depends a little bit on the speed of your actuators. But this is something that would generally run in the evening or at a period where we can stroke that damper from min to max to profile the entire performance of that damper assembly. So this is a portion of the math that makes it pretty easy to understand. When we're going through learn mode for any given position, here we just chose 30%, but again, it's just a given position in space. If I know all 3 temperatures, we can calculate with that ASHRAE 111 formula what the percentage of OA is. Here, for 90-degree OA, 70-degree return, and a mixed air of 78, we know there's 40% OA present in the supply airstream. Turning that around for a measurement based on the performance curve, again, if we're at any given inclinometer position, here we happen to be at the same one. If I have a good supply air total, I can look up with the chart to say my characterized airflow at 30 degrees position was 40%. 40% of 1,000 is 400. The balance would be coming from the return. So the same type of equation lets us profile while we're learning, and then the same math based on the performance curve gives us the measurements when we're actually reading airflow. And I'll come back to that guideline 36, that this is the exact method that they want to run all of the fall detection for these high performance buildings off of. The benefit here is when we're actually producing airflow measurements with the airflow curve, we're giving you, and I have delta T, we're giving you two OA measurements, one from the performance curve, which would be the standard measurement. We'll run the delta T measurement or the mixed air temperature equation measurement in the background, and we want to see those be very close together. If we see a split between those two numbers, my OA by temperatures does not match my OA by table, we know there's something that's mechanically changed or damaged with the equipment, and it needs to be serviced. You know, maybe a piece of cardboard stuck in the inlet, or if we lost a damper blade, or now my return damper is not moving and actuator seized, economizer is not working. Any of these conditions will cause a split in the temperature, or the difference in the OA by temps versus the OA by table. TrueFit actually recently qualified for the California Energy Commission's economizer fault detection certification. The gist of that certification is they want to ensure that economizers are functioning normally in California. Energy is very expensive, and the integrated diagnostics here let us qualify for that certification on our product out of the box. So kind of an exciting feather in our cap. So one thing you'll hear me say a lot, if you've heard me talk about airflow stations, is one, the temperatures don't lie. That's why ASHRAE tells us that we need to use them. And two, the proof's kind of in the pudding. So there's a few performance charts we have, some job installs that we've cataloged and poured over, and they're good examples of our technology versus some of the other competitive technologies that are out there. The first chart I'm going to show you is an office building in Connecticut. There was a couple already installed airflow measurement devices there. They were installed by a professional, balanced by a third party before we were there. The damper was modulated from min to max. I'll talk through some of that performance. And then we have the same system during a period of inclement weather. So normal operation first. The black line here is damper position. So we start with left to right, something that's about 2/3 open. And then we close it down to a minimum position in the second half of the chart. The yellow line here is that ASHRAE 111 equation. So again, this is the balancer number in real time. We see a little bit of lag after the damper moves as those temperature sensors acclimate, which is normal and to be expected. That's one reason why we can't just use a temperature measurement out of the box, why we need that characterized airflow performance measurement, because our measurement is instantaneous. And there is times where we don't have delta T in the building, so we need some of a reference, which is the inclinometer and that performance table. So here, competitor A, this was thermal dispersion. This is following the trend, I'll say, on the first half of the chart. Again, when the damper is mostly open, my air velocities are high. And that's typically where these things would be calibrated, is at a mostly open airflow. The interesting thing here is when we close that damper down, we see the competitor A get a false floor. This is about 6,000 RPM on a 22,000 CFM air handler. So that's a pretty significant offset that they had. And we see even as we step that damper back open, those air velocities are low enough where they're not going to register any new measurement there. Competitor B is also a thermal dispersion. They're following the same trend line again when that damper is mostly open. The interesting thing for competitor B is when we close that damper down, the airflow velocities are where they don't get any reading and becomes a little bit of erratic before it picks back up here at about 20% damper position. So all in all, you know, they're producing a measurement when they're open, but typically where we're going to control down at that minimum ventilation or mostly closed state, you know, we're either going to lose one for overreading and driving that damper more closed, leading to underventilation, or in the case of the green line, we're going to drive that damper open and overventilate our space, trying to get back to a registered measurement. The blue line here is TrueFit, and we're following that Asher 111 equation spot on. Again, we're using the same measurement to profile the equipment and produce that table. So you can see that the performance really pays off. As we close that damper down, and we're getting getting to that 111 equation very quickly, even before the thermistors acclimate. And then when we get to, at 10 and 20% damper position, we see that those numbers are right on top of each other. So this was the same system during a period of rain. Typical OA would be designed at a low enough velocity. We shouldn't be pulling in contamination and moisture and things like that. Especially with thermal dispersion, even with temperature sensors, anything that affects that thermal mass equation is going to affect the quality and repeatability of their measurement. I think anybody that's done OA measurement with thermal dispersions, like in a hood of a rooftop, has probably seen charts that look like this already. Same legend here. So competitors A and B are green and red. The red measurements are everything from 19,000 CFM to 9,000 CFM. So pretty big swings and not a lot of time. Again, we're adding moisture to those thermal dispersion thermal dispersion elements, and it's affecting the quality and repeatability of their measurements. For the Asher 111 equation, and we see we're pulling in enough moisture where we're also affecting the temperature measurements, but the rough amplitude is, again, right on the blue line. So I'm pretty confident that our numbers are right where they should be. We've had a lot of chances to install TrueFit across the country. One of them was the University of Texas Medical Branch down in Houston, where they have class 3 and 4 containment labs for researching things like Ebola and infectious diseases, places we probably really don't want to be as people or occupants in those buildings. But in order to qualify to be on their networks, we had to go through an independent test at a certified lab that they use for all of their airflow measurement devices and balancing. And at the end of the day, what came out of that certification was that TrueFit is within 3% of airflow at the full range of damper positions, supply, return, and OA. So it's a little bit of an eye chart, but you can see, again, as expected, as we step that damper up, our supply stays fairly steady, our OA goes down, our return goes up, and they always add up to the proper total supply because of the nature of our measurement. So to wrap up, I'm going to show you a few different installations that we've done that are representative of common places where our product has gone. A number of rooftops, unit ventilators, but even large air handlers. So on the rooftop front, this is a packaged rooftop here at KMC headquarters. We have these running in both variable and constant volume applications. Everything from the tool room, grinding room, to office spaces with VAVs. We've taken supply air measurements with both fan inlet and pitot arrays. Fan inlet's generally favored. It's easy to get to. It's a very high velocity, very repeatable signal. One of the easiest places for a balancer to calibrate, again, because it's a high velocity, easily accessible application. So installation here on this rooftop was about 4 man hours, and then it was learned, and it's integrated into our building management system here at the office. So a couple pictures here. This one, the inclinometer we see is on that return flap. It was tight and geared to the OA damper. We have a modulated actuator controlling that mixed air damper assembly. And then on the right, you see a pitot array, again, getting that fan inlet total supply air there. And again, at the end of the day, as we modulate that damper from min to max, we see that the OA goes down, the return goes up, and those two always will add up to the proper supply number. So all of these measurements coming out of that one airflow measurement system that we put in. The next study that, or next building I'll show you, it was Pine River Schools. This was a bunch of unit ventilators in northern Michigan. And you'll see here there was a 400 CFM UV and a 600 CFM UV. Same pieces and parts that go into rooftop. We're going to go into that unit ventilator, but I don't know of any other technology that can accurately measure the airflow in that unit ventilator. Again, because the temperatures don't lie. And there's not restricted by turbulence or laminar flow restrictions there. So we've done a few other unit ventilator jobs. One was a pilot in California, and the code out there, I see this happening across the country, is that, again, when students are in the classroom, they have to guarantee that there's so many CFM coming into and out of that space. So the competitive situation was they were going to install an ERV and physically pump air at the ventilation rate into and out of the building. When we applied our TrueFit AFMS to that unit ventilator, we actually found that they were meeting their ventilation minimums just in the leakage of the unit ventilator themselves. Again, temperatures don't care where that air comes from. So we're giving you credit, or we're giving the building credit for any leakage through the damper, through the face, that sort of thing. Anything that affects that mixed air equation number, you get credit for. So in this case, we actually could close down the OA damper even further. And at this school system, there was approximately 500 unit ventilators in the district. And again, they have a fairly high electricity rate, but they are projecting that this AFMS with the energy savings was going to save them over 700,000 kilowatt hours a year. And they were going to avoid the mechanical expense of installing all the ERVs to guarantee that flow. The last one I'll leave you guys with before we take any questions. Again, if you have questions, just put them in the chat, and we'll grab them here in a second. But this was a whole building air handler in Chicago. The school is right down the street from Wrigley Field, so it's a fairly picturesque part of town. But this was a 55,000 CFM air handler, built-up air handler in the basement of the school. Installation was about 5 man-hours. It was all union labor in conduit. There was existing Ebtron already in the building to compare to. So again, nice looking school right down the street from Wrigley Field. And this is standing in that mixed air chamber. So you'll see that if you really look at the bottom, there were 3 outdoor air dampers, each with airflow measurement already installed. This is a pneumatically controlled air handler. So we see the pneumatic dampers or actuators here all gang together. The return is on the right. This was a dual delivery air handler. So actually had 2 return dampers, one from the east side of the school, one from the west. And if we look at the fan, this is about an 8.5 foot inlet, about a 12-foot fan, and then half the airflow got split off for, again, each half of the building with independent heating coils. To run the AFMS, all the pneumatic control was maintained. We E to P'd the damper signal into the AFMS and then E to P'd it back out. So it's still pneumatically controlled, pneumatic muscle moving the dampers. We're just producing airflow measurement with BACnet and trending it in their front end. And the results of that installation were, we have the Ebtron existing measurements on the left, KMC or the TrueFit measurements in the middle. If the outdoor airflow measurements that were existing, again, we got 3 total, 1 for each damper. We see that one of them is a lot higher than the other. We had the same balancer that would that commission these come out and commission ours. And he said the way that he measured that was once he calibrated the supply, he drove the OA dampers 100% open, return dampers closed, and then turned the gain up on one of those dampers or one of those flow stations. So that way the total OA matched the total supply. I think that that's how most people would do it, save any other method. The problem with that is, again, that did not account for any leakage that they're getting through the return dampers or the cracks in the doors or even the cracks in the damper louvers. We see that if we go back to these pictures, we see quite a lot of light coming through those return dampers, and there's a couple bigger doors for access on either side that you'd see light come through as well. So what that means for the school is that when we fired up our AFMS and characterized their system with that characterized airflow performance, and based on the temperatures don't lie, we found that at 100% outdoor air damper position, we're only getting about 35,000 CFM of OA. 17,000 is leakage through a return path of every kind. What that means to that school is they're under ventilating where they thought by a third. Again, in the era of high performance buildings and COVID mitigation, infectious disease mitigation, that's a big deal to be under ventilating by that much. So the last chart here is our last picture is just trend data coming out of our IoT software platform that was on top of this this building automation system. We see that there's a total OA again of 52,000. OA is in red, supply or return is in green, and this yellow line is that OA by temps. So we see that when we have proper delta T, we begin calculating what that number is, and we see that the OA by temps match the OA by table, as we would expect. So to wrap up here, several market technology challenges that we've covered briefly today. Not all airflow measurement is fit for all types of systems or restrictive ductwork. A lot of times they don't produce consistent results. None of them are based on ASHRAE 111, and a lot of times that leads to higher cost of ownership, whether that's installation, commissioning, ongoing maintenance. They can have limited options for integrating into your control system. I think we've talked a little bit about why our system, that TrueFit AFMS, is a little different, has addressed those concerns. We have compatibility with any equipment type, any ductwork configuration, accurate and reliable data that's not affected by contamination and things and turbulent airflow that you'd find in most types of equipment. So the last slide that I have before we go to questions, again, different technologies are meant to be applied different places. In the world of outdoor airflow management, TrueFit really is a great fit for all of these types of systems. The other technologies out there, whether they're orifice plates or thermal dispersion or duct arrays of pitot tubes, all have their place. They all work if they're installed in the proper location and given a chance. The problem is, as an industry, I think we put technology where we have to, not where we're supposed to. And again, that creates a lot of the system inaccuracies and repeatability issues that TrueFit was born to address. So with that, we can grab some questions here.
Awesome, Eric. Looks like we have one question, and you might have hit this while we were going, but if we're accurately measuring the total supply airflow and the inlet mixed air temperature, why do we need the inclinometer?
For sure. So we could run those temperature equations in real time. That's exactly what we do for our diagnostics. However, there are many times where we don't have delta T. And if we don't have delta T, we can't run those numbers, which is why we need the performance curve and we need to know where we're at in the curve, which is what the inclinometer tells us. So those two things are key to producing measurements at any time, regardless of the delta T that you actually have in your system.
Got another one here for you. This is a good one. Are there any available grants for this technology for schools?
Yeah, we have seen across the country that depending on your utility, we have seen utilities do rebates and things for that. The best thing I could recommend there is, work with Gardiner, or your technology provider in your local utility. Most of the time, because it's outdoor air and it's commercial, and there's a pretty good energy savings there if you're not accurately measuring already. Generally, they've been open to listening and coming up with a situation where they'd be interested in a rebate.
Awesome. I don't see any other questions. If there's anything else, please type it in the box. Chat box, that is. I don't see any coming in, so it's 12:41. We can go ahead and depart. Thank you very much, everybody, for attending. We appreciate it. Please reach out anytime if there's any additional questions or follow-up we can provide. Everybody have a wonderful rest of the afternoon and week.
Thanks, everybody.
Thank you.